Recording. All right. So, a couple of notes. I won't see you at all next week. Monday, because there's no classes at all. Campus. And then Wednesday, I'll post a video instead. Okay. And so, depends on how far we get today, and then I'll pick up there and finish chapter 7 in the video. And so, hopefully it'll just be a little bit, but we'll see how we do. And we ended off leaving some examples. I said, hey, we can do these for review on Wednesday. Try them on your own. We introduced my slots, as I call them, right? And so these slots are pretty useful for figuring out how to count options. And so I'm just going to jump right in. We did talk about sets, and we introduced terminology associated with sets and Venn diagrams, right? Counting with Venn diagrams. But we'll kind of leave that alone for a little bit and just pick up with the slots that we introduced. So, in how many ways can a 3-question true-false test be answered? And so I'll state the assumption here that must give an answer. Right? If you're kind of thinking critically, you might say, well, you could leave it blank, but why would you do that? Right? And so let's assume that you have to give an answer in this true-false test. If you have 3 questions, you could have Q1, Q2, and Q3. What I want you to do above, right? Because you have to answer question 1 and question 2 and question 3. And so here, and remember when we say and means multiplication. Sometimes it's hard to pick out when you should be saying and today we'll introduce or, which would be addition. But sometimes it's obvious, right? You have to answer question 1 and question 2 and question 3, right? And so what we get is, if we're saying and in between, now let's see if maybe just linking them makes it happier. I'm going to multiply across, and above each question, I'm going to jot down how many options I have for question 1. Well, in a true-false, I only have true or false, so I have two options, right? And same thing with question 2, and same thing with question 3, which means I have 8 ways that I can answer, 8 different ways that I could answer a multiple or a true-false 3-question problem. Any questions about that one? Now, this one is just slightly different. What's this one going to look like? In how many different ways can 4 people be seated in a row? So now I have 1, 2, 3, 4 seats. Let's say seat 1, 2, 3, 4. When I'm drawing the slots, you can just assume that you're going to multiply through. Now, here's the pickle. If you have 4 people, right, then for the first seat, you have 4 people to choose from. Right? And so what we get is we have 4 people to choose from for the first seat, but now one of those 4 is seated there, right? Which means that I have only 3 people for the next seat. And by the same logic, then I only have 2 people left for the third seat. And finally, I only have 1 choice for the fourth seat. Okay. I'm gonna go with 24. Okay. I will make a note here. Since 1 person is already seated, we now have 3 people to pick from. Okay. And then etc. for the others. Okay. Same logic. Do I want to do this? Sure, why not? I'll make a note here. Note, we'll see it more, but 4 times 3 times 2 times 1 is called 4 factorial. Is the same as 4 exclamation mark, 4 factorial. Okay? And so here, 4 factorial. This factorial might be new, right? You might have seen it, might be new. Okay, but all it does is it says, hey, starting at 4, do everything minus 1 until you get to 1, right? And multiply it through. So starting at 4, 4 times 3 times 2 times 1. And so here, so as an example, 5 factorial would be 5 times 4 times 3 times 2 times 1. So starting at 5 in this case, right, multiply by decreasing by 1 until you reach 1. Starting at 5, I'll say means starting at 5, multiply by decreasing by 1 until you reach 1. And we'll see that more today. Yeah. Good. You got it. So we'll see more of the factorial in the next section, but thought it might be nice to see it here, right? In fact, a lot of the next section, which is just lurking down here, permutations, a lot of these problems can be solved with just the slots. So if you like the slots, then you'll be able to solve a lot of problems just using the slots, right? Or rather, if you embrace the slots, they will serve you well. So, how many 3-letter word sequences can be formed using the letters A, B, C if no letter is to be repeated? Now, when we say word sequences, they don't have to be words, just combinations of 3 letters. And so here we have just letter 1, 2, and 3. If no letter is to be repeated. Well, for the first letter, I've got A, B, or C to choose from. So I have 3 choices. But if no letter is to be repeated, right, then I only have 2 choices left for the second one. Yeah. Oh, I thought it was like a pause, stop. Yeah. 1. That's what it was. Got the hang of it. Nice. So 3 times 2 times 1 puts me at 6. Oh, it's letter number 1, number 2, number 3. I could tell, even as I wrote it, I thought that is kind of confusing. And I should do seat number 1, number 2, number 3, and number 4, because that's the one I first reacted to. Nice. So kind of fun, right? A really common problem that we saw last day is the license plates, right? Sometimes there are restrictions on license plates, right? And so in BC, let's, hello? Let's see here. A common problem involves finding the number of possible license plates. Cars in BC now. Cars, not trucks. Cars in BC now follow, what is it? Thinking of my own. Alpha, alpha, numeric, 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 alpha. Letter, letter, number, 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 letter. Yeah. It used to, it used to be, well, I've seen both. So we've cycled through. We had 3 letters followed by 3 digits. And then before that, I think we had 3 digits followed by 3 letters. So they mix those up. Obviously, those are different. But if we think about alpha, alpha, numeric, 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 alpha, how many plates do we have? Lots. Alphabet, 26 letters in the alphabet, times 26 times there are 10 digits, right? When we talk about digits, we usually say numeric, but alphanumeric, but digits there are 10, yeah. But you don't want to forget about 0. I know. That's the tricky part. You caught me just before I made the note. 0 through 9. And 26 letters. Times some more. Times 10, times 10, times 26. I wonder how many? 26 times 20, oops, times 36, no. It's big. 1,757,6,000. 1, 2. 17,576,000 plates. There's a lot of them. A lot of plates. And we're already, because for some reason I have a fascination with license plates, and I've noticed we're already on the Zs for the first alpha, and they do them chronologically. So anyways, little fun fact, I guess. There are some combinations that I think they remove, right? Kind of if it spells something bad, or, you know, you get it. There's some that they don't put out there, but in general, 17,576,000 different plates. Crazy. And that's just with the new system, right? New naming system. So let me see here. Let's talk permutations. What we were doing is called permutations. And so, especially here, when we were talking about, okay, 4 people seated in a row, right? And I incrementally remove a person because they're already seated, right? And it doesn't matter who's been seated. And same thing with the letters, right? A, B, C, no letter repeated. How many 3-letter word sequences can I make, right? 3, 2, 1. Those are what we call permutations. And so we talked about the sequences, the word sequences, using the letters A, B, C just now, if no letters repeated. You could make a tree diagram. Should we do it just for fun? Yes. Let's do it. We will see tree diagrams again in the next chapter, and so it's worthwhile talking about the tree diagrams. But in this case, I think the slots are a lot easier to think about. But for your first letter, letter 1, you have 3 options, A, B, or C. If your first letter was A, then, and let me just move this over just a smidge here, then you only have, I'll do a shorter, like here, 2 letters left that you could choose from. And so letter number 2, if the first letter is A, then you have B or C to choose from. If the first letter is B, then you have A or C to choose from. And if the first letter is C, then you have A or B to choose from. Now, of course, depending on the branch that you headed down, right, there's really only one option, right? If you've done A, B, then the last letter has to be C. If you've done AC, then the last letter has to be B. B, A, C, B, C, A, C, A, B, C, B, A. And usually what we do is we write the combinations down below. And so you read them down each branch, and then you'll have listed all the different permutations. So A, B, C, A, C, B, BAC, BCA, CAB. Hey, a word, cab. CBA. I read this novel one time called A Short Stay in Hell, and it's about well, it's made up obviously, but where hell is a library with a book that's 300 pages, and it's all the letters just permuted like this, and you had to find the book that told your life story. But just finding a word, that's why I thought of it. Is hey, a word, cab. That's so exciting. Now imagine you have to find a sentence. Oi. Right. Infinite number of books. Not infinite, but a huge number of potential books. Anyways, kind of a weird novel, but I guess I'm thinking about it. So that's something. So from our tree diagram, right, we found these 6 combinations, right, or permutations, I should call them, because arrangements like these, and I'm going to double underline where order is important, okay, and no element is repeated, that's what we call a permutation. And so these are all permutations of the 3 letters. And so order is important because ABC is different from ACB. Whereas if order wasn't important, these 2 would be the same. Right? Well, they would all be the same, I guess. Okay. Nice. So a permutation, as a definition of a set of elements, is an ordered arrangement where each element is used once. Okay. Good. Let's see. Do we have an example? I wanted to clarify this one here. Well, maybe I won't because it's gone. How many notice 3-letter word sequences can be formed using the letters A, B, C, D. So now I have 4 things to choose from, and I only need 3. Again, the slots are going to work here, right? Because if I want 3, then I have letter number 1, letter number 2, and letter number 3. I have 4 letters to choose from initially, right? And so I have 4, and then I have 3, because I've added a note here. We're going to assume no repetition here. Okay. And then 2. Doesn't have to go to 1. That's okay. We only needed 3 letters. Like 3, 2, 1. No, because we have 4 to choose from. So you have to start picking from the 4. Yeah. And here 4 goes there. Good. Although multiplying by 1 doesn't do anything, we wouldn't put it down. It's weird. Yeah. But it wouldn't change the answer. 4 times 3 times 2, I'm gonna go with 24. Oh. What if you could repeat it, right? Assume that you could draw from A, B, C, D again, right? Then that would change it, right? Then you would have 4, and then you would have 4 again, and then you would have 4 again, right? And so then you'd have more options, right? Yeah.
In that case, like technically, would you, if you didn't have repetition and repeat, could you do a little tree diagram and you could put A, B, C, and D, just like you did?
You could, but if you're allowed to repeat, then it's going to be really, really big, right? Especially if you have A, B, C, D, then you would have 4 branches, and then each of those would have another 4 branches, 4, 3, 4, 4 branches on each of those, and then another 4 branches. And so, although you can do that, right, it's kind of fun, a little bit tedious, I think the slots are a little bit easier. Because then you would just do 4 times 4 times 4. But it would make a huge tree. But you could do it. You can do it if you wanted to. Permutations of the letters of the word article have consonants in the first and last positions. Now, consonants are non-vowels. Vowels, we are going to say, so I'm going to define it here. Consonants, or maybe I'll say, wait, hey, yeah, big. Note, consonants are not vowels. And let's assume, because there's some debate, I think, or at least there was when I was growing up. Let's assume vowels are A, E, I, O, U, and sometimes Y. I know that's still the saying A, E, I, O, A, E, I, O, U, and sometimes Y. That's not helpful. Let's assume that vowels, Y is a vowel. Obviously, I'm not going to ask you about consonants and vowels without telling you what they are on a test. So if I wanted to ask a question like that, I would tell you if Y is considered a vowel or not. Okay, how many permutations of the word article? So first thing we want to do is we want to figure out, okay, well, that's just taking all those letters and rearranging them in all the different ways that we could. And we've added some restrictions. So first thing we want to do is figure out how many slots we have, right? How many letters do I have? And so I've got 1, 2, 3, 4, 5, 6, 7 slots. 7 slots to fill. So I'll start with drawing my slots. 1, 2, 3, 4, 5, 6, 7. Now, if there are 26 letters, and 1, 2, 3, 4, 5, 6 of them are vowels, 6 vowels, then we have 20 consonants. In general. How many vowels and consonants do we have in article? Nice. I hadn't even done it yet. I guess I will need more space here. Let me just add a page this way, maybe. And maybe I'll move these slots down just a little bit. Article. Has 1, 2, 3 vowels and 4 consonants. We have to have consonants. We have to have consonants in the first and the last positions. And so how I like to do it is I'm going to force fill the first and the last positions with consonants. And now I have 4 consonants to choose from for the first position. And then I am left with only 3 consonants for the last position. It doesn't matter, since we're multiplying through all these numbers, right? It doesn't matter whether this was a 4 or this was a 4, right? But one of them has to be less than the other one. Now, I've used up 2 of these letters, which means I have 5 left over, right? And there are no other restrictions, right? I have to have consonants in the first and the last positions. I've dealt with that. So now I can just start with any number here. Oops. Any. Oh. So if I've used up 1, then I can move on. 4, 5, 4, 3, 2, and then my last letter can go there. Yeah. Go close the door.
Well, I was just confused by you went to put 20 letters, but I guess article does not put the 7 letters.
That's
So,
that's the ticket. That's the ticket. So here I made notes in general, and maybe that was confusing, but then we just focus on article.
yeah, and then why wouldn't you have like the number 6 and 7? Because you have 7 letters, I understand, and then 3 vowels, so that brings it down to like technically 4, but then you put 5 in there, and then that can be.
Oh, because from any, so we've used up 2 of these consonants, right? And so 2 of these guys, 2 of these have gone here and here. And so now I have 2 plus 3 of any of them left. And so here, 2 plus 3 remain. That one's sneaky, so. Maybe I should make a note here. start with the restrictions. Kind of handle those first and then see what's left over. We have 5 letters, A, B, C, D, E. Then if we want to find the number of 4-letter word sequences, we can do that. The number of 3-letter word sequences, and then the number of 2-letter word sequences. We can do that, right? And so for A, 1, 2, 3, 4. Letter number 1, number 2, number 3, number 4. Notice how I got lazy here and I didn't write the multiplication? That's okay. In fact, I guess I didn't even solve it. That's probably not okay. We should do that. You can be lazy to a point. Let's 4 times 5 times 4 times 3 times 2 times 1 times 3. 1,440 arrangements ending in a consonant and beginning with a consonant. Still a lot. And I'm going to say assume no repetition is allowed. Otherwise, it'd be really boring, right? 5 times 5 times 5 times 5. I guess it's still kind of boring, but in a different way. So for 5 letters, first letter I have 5 choices, then 4, then 3, then 2. Oh. For B, if I have 1, 2, 3 letters, number 1, number 2, and number 3, I still have 5 to start. Then I have 4, and then I have 3. 5 times 4 times 3, 60. And then finally, two letters. Letter number 1, letter number 2. Still have 5 to start. 4. So these are all permutations. Yeah? And so we'll have a formula that we could use to solve these. Yeah? We could use the permutation formula. Permutation formula instead. I tend to not use the permutation formula that often, and so because I prefer the slots, but I should introduce it. since it's the entire chapter. Or section, I should say. So, permutation formula. The permutation formula, you might have seen at some point something like NPR. So the permutation formula, NPR, and if you look at your calculator, there's an NPR button usually. So before we give the formula for NPR, we have to introduce the factorial. We've already seen it, and so we're not really introducing it, but here we are introducing it officially. And so in general, n factorial, n factorial is n times n minus 1 times n minus 2 times n minus 3 times dot, 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 all the way until you reach 1. Right? And we've already seen 4 factorial, 5 factorial, right? So you start at the number, and then you keep decreasing by 1 until you reach 1. Okay? And so here's a fact. 0 factorial is 1. That's kind of weird, but it is. So that's neat. So we've seen the factorial, right? And many calculators have a factorial button, which you can try to find if you want to. We won't really need it, so it's okay. Okay, now we're ready for the actual permutation formula. So the number of permutations of n objects taken r at a time, right? And so if we translate that to this question here, right, I have 5 objects taken 4 at a time, then 3 at a time, and then 2 at a time, right? So what we could do is we could use this formula, right? So NPR, so it's a lowercase n, capital P, lowercase r. And most calculators, even basic calculators, have the button. So most calculators have an NPR button. So we're told that NPR looks like n times n minus 1 times n minus 2 times n minus 3, all the way up to n minus r plus 1. Let's grab this one here. Copy. Recall from earlier, this is the same as n equals 5, right? From 5 n objects, so 5 objects, and we want to take r at a time, right? And so in this case, with 4 letters, we want r equal to 4. And so if we use this formula, 5p4, copy this. Oh, and I need more space. Always more space, I guess. Hey. So we want to find 5p4. Where you see an n, you're going to replace it with 5, and where you see an r, you're going to replace it with a 4. Oh. And so we start with 5 times 5 minus 1. And maybe it'll be cleaner if I just write 4 right away. And usually I like to do this last one first so I know when to stop, right? And so n minus r plus 1 in this case is 5 minus 4 plus 1. So I'm going to stop at 2. So 5 times 4 times 3 times 2. Nice. That's the same. 5 times 4 times 3 times 2. Notice that that's the exact same thing that we found. So again, if you get comfortable with using the slots, there's no reason you can't use the slots, right? So if you don't like the permutation formula, that's fine. I don't either, because I prefer to use the slots. Right? But if you like the permutation formula, if you've seen it before maybe, and you like it, go for it. So here, notice this is the same answer we found with the slots, or found using the slots. I'll say you may use whichever method you prefer. Another way that we could write out NPR is like this: n factorial divided by n minus r factorial. Yeah? And this is what's on your formula sheet, which has been pushed down here. So this is on your formula sheet, the permutation formula, NPR. Some calculators call it PNR, right? So just be comfortable with however your calculator works or looks like, I guess. N factorial over n minus r factorial. So this version is on your formula sheet. Oops. Now you don't need to use it to solve these counting problems, but there are instances where I want you to use this formula to show me that you understand how the factorial works. And what you're going to do is there's a trick. There's always a trick, isn't there? A trick. And maybe I'll bring in the one from the formula sheet so that we can see it. Mm-hmm. Uh-oh, now I've done it. Copy. It's because it says compute using both formulas. So I guess I should have them on here. Let me just clean this up. So this is formula 1, formula 2. Compute the following using both formulas. So we're going to, yeah.
Can I just put it into my calculator? And then I just think about the formulas because it was the other one.
So this is just an exercise. I do want you to be able to simplify something like this without your calculator. I'll show you what I mean. I know, right? There's a trick, which is why I want you to do it on the test so you can show me that you know the trick. I know, rude. It is. What's nice though is you can check your work. With your calculator. That's nice. With our first formula, my n is 6 and my r is 3. And so, like we did earlier, I'm going to figure out where I need to stop, right? And then just start at 6 and keep going to that point. And so here, stop at n minus r plus 1, which is 6 minus 3 plus 1, which is 4. So then I have 6p3 is 6 times 5 times 4. Six times 5 times 4 is 120. I encourage you to check your answer using the NPR button on your calculator. And because all the calculators are all different, if you want to know how yours works, because sometimes you have to put the N in and then hit the button. Sometimes you hit the button and hit the N and the R in together. So it depends. Get to know your calculator, I guess is what I'm saying. And I'm happy to show you after class. What about using the next formula? N factorial over n minus r factorial. So 6p3 is 6 factorial divided by 6 minus 3 factorial. So 6 factorial divided by 3 factorial. What you're going to do is write out 6 factorial until you reach 3 factorial, because then you'll be able to cancel, right? And so here, write out 6 factorial until you reach 3 factorial. 6 times 5 times 4 times 3 factorial. 3 factorial is just a placeholder for 3 times 2 times 1, right? So you don't have to write that. Because now now we can cancel. Three factorial. And then you're left with 6 times 5 times 4. So that's the trick, is just writing out until you reach the value in the denominator, and then just cancel those and get rid of them. Right? 6 times 5 times 4 is hopefully still 120. Nothing changed. That's great news. So now that we know the tricks, let's do 7p2. Seven P2 is, well, I guess I should figure out where I need to stop. Okay, one more line. Copy. Stop at 7 minus 2 plus 1. Nice. Oh, that's nice. 7 times 6, I guess. Okay, yeah. 7 times 6 is 42. Oops. What about, this is the formula that I'm more interested in, right? Because this is the one on your formula sheet. 7p2 is 7 factorial divided by 7 minus 2 factorial. Seven minus 2 factorial is 5 factorial, which means I'm going to write out 7 factorial until I hit 5 factorial, and then I can just cancel them. And so I get 7 times 6 times 5 factorial divided by 5 factorial. Ding, ding. And 7 times 6, still 42. You look at your formula sheet. These are the only two formulas. So this is the combination formula, which we'll see in section 7.5. So that'll be in the video that I post for next week. Okay. But notice it's very, very similar, right? And so on the test, I need you to be able to simplify these formulas like we've been doing, right, without using your calculator. You can check your answer with your calculator, right? But you have to show me that you know that trick to cancel values. You know? It'll say use the permutation formula or use the combination. Nice. Any questions about those though? Or we keep going? I'm curious to know what time it is. Oh. The night is young. Well, it's so dark out. People are leaving. I don't know. Who knows? The yawn. Although I get the yawn. Been yawning all day.
I'd be.
I was waiting all day to take the dog out and until it was nicer out. It never got nicer. So I just had to take her. She was like, I hate this.
That's how I felt today outside.
Right? Yeah. It's cold, it's gross. It wasn't raining that much, but ugh. In how many different ways can 4 people be seated in a straight line? And here's the kicker, if 2 of them insist on sitting next to each other. Okay, so these 2 are the troublemakers. No, they're the BFFs. They want to sit together. That's okay. Just for simplicity, let's call these A, B, C, and D. They're different people. Let's give them all different letters. Now, it doesn't matter which 2 are sitting together. They're just always going to sit together, right? And so if 2 of them insist on sitting next to each other, let's say A and B want to sit next to each other, then what we can do is we can say, okay, fine, I'm just going to treat this as if it's one person, right? They get 2 seats, but we'll just kind of pretend it's 1 seat for now, and then pull up a chair, right? And so that's going to be the sneaky part. Okay? So let's say A, B, and treat them as one person. Okay? Which means that now, effectively, we have 3 things to choose from, right? And so now I have seat number 1, number 2, and number 3. So here I have 3 things to choose from. 1, 2, 3. Treating them as one thing. Then I have 2 choices, and then I have 1. Which means I have 6 total options. What we need to consider is that this was thinking about A, B in that order, right? But they might say, hey, no, I want to sit on the other side, right? And so here, this is with AB as, oops, sorry, AB as 1. What about, or we could have B, oops, BA as 1. That's going to be a different seating arrangement, right? BACD versus ABCD, and so on. And so then what we have is we have seat number 1 again, number 2, and number 3. Now I have 3, 2, 1 again, which is still 6, but it's a different 3 that I have to choose from. So here, when we say or, we add the options. So there are total. Maybe I'll just. Just move it down. So there are a total of 12 options. Yeah, sorry.
Do we have to do it in like prefactorial order, or can we do like 1, 2, 3?
You can do 1, 2, 3. I tend to start with the highest number and then chip away at them just to make sure I'm not missing any. But yeah, there's nothing wrong. You can do 2, 1, 3 as long as you, but that's crazy, right? That's crazy. Since you're multiplying, it doesn't matter. Nice. So that one's a little bit tricky, right? But if you've got things that have to stay together, then you can kind of force them together. But notice that if we did 4 slots, right, 4 people and 4 seats, then it's really hard to make sure that these 2 people sit together, right? Because then you might have one at the beginning and one at the end, right? One in the middle. And so treating them as if they're one thing is going to be how you solve it. What if, consider this scenario, you probably have something similar at home, but probably more than 4 math books. Well, I have more than 4 math books. You might have more than 4 other books. I don't know. I have a lot of math books. Not to brag or anything. I actually have more stats books than I do math books, but you have 4 math books and 5 history books. That might be true. To put on a shelf that has 5 slots. In how many ways can the books be shelved if the first 3 slots are filled with math books and the next 2 slots are filled with history books? There's not really a trick with this one. 1, 2, 3, 4, 5 slots. And the first 3 slots are filled with math, math, math. And then the next 2 slots are filled with history and history. You have 4 math books. So you start with 4. And then you've used 1, so then you have 3, and then you have 2. Now you can move on to your history books. You've got 5 to start with. 5, and then you've used 1, so then you have 4. Four times 3 times 2 times 5 times 4 is 480. You could use permutations here. I don't really recommend it because I find it more difficult. I'll show you. Or use permutation, use the permutation formula. Which would look like this. So from 4 math books, you want to fill 3 slots, 4p3. And, so and means multiplication. So times, because it's and, 2 slots with history books. So from 5, pick 2. If you were using this formula, you're welcome to use your calculator instead of the actual formula, right? And you'll find that it's the same answer, right? 4p3 is 24, and I'm trying to keep it on the same page, but maybe it's futile. 5p2 is 20, which is 480, right? So you're welcome to do it that way. There's nothing wrong with that. I just have a hard time personally to pick out what it is I need to do with that. Whereas the slots, to me, make it more obvious. But maybe you're not like me. Maybe you're cooler than me. How about now? Okay, nice. Any questions about permutations before we just level up slightly with some circular permutations? Hmm. Oh, I shouldn't have said level up. Circular permutations are kind of neat. Yeah. So if we have three people, A, B, C, let's say, and if we were more awake, we would get together and we would put groups of three and you'd stand in a circle and tell me how many different permutations there are, right? How many different ways could you sit in a circle, right? Turns out there's only two ways for three people, right? And so in a straight line, right? If you had three people in a straight line, you would have 1, 2, 3, 3, 2, 1, which is 6. Right? That's what we just worked on. So in a straight line, you have 6 different ways that you can arrange these three people. Right? Now, we're putting these slots in a circle. Right? And so now, it doesn't actually matter where you start. Huh? So if we start with A here, then I can move to B, and then I can move to C, and then I'm back at A, right? Or if I start with A here, doesn't matter which slot, okay, then I already started with B, so that kind of eliminates that option. So then my next option is to start with C, and then I go to B, and then I go to A, right? And so there are only 2 ways that we can seat 3 people in a circle. So this is a circular permutation. And the key to understanding it is that no matter where the first person sits, then it doesn't matter. All you're doing is twisting the circle, right? And so what we do is, where is it? In circular permutations, the first person is a placeholder. So you just pick one person, right? And then there's only one option for that placeholder. And it doesn't matter where on the circle they sit. And then we talk about how everyone else behaves after that. Yeah? Now let me add a page this way, maybe. Nope. Now, I will make a note here because the textbook goes through and develops a proof why the number of permutations of n elements in a circle is n minus 1 factorial. But for us, as long as you remember that, then you're okay. Okay? So, for a more comprehensive proof, see the textbook. But the idea is this. Let's say, for example, we have 3 elements because we just established that there's only 2 ways that I can do that. So then what I can do, if I think about it in a circle, right, then now let's see if I can draw these slots in a circle. 1, 2, 3. Be more fun if there was more people. But the key is the first person is considered a placeholder. Okay? And so it doesn't matter where he sits. And so the key is that you place, there's only one option for the placeholder. One option for the first person. Which means that we have 2 left and then 1. So if you kind of move through the circle like this, 1 times 2 times 1, 1 times 2 times 1 is 2. Which, if we have 3 elements, 3 minus 1 factorial is 2 factorial, which is 2 times 1. Right? So, or 3 minus 1 factorial, which is 2 factorial, is 2 times 1, which is 2. I point this out because it's not on your formula sheet, right? The n minus 1 factorial for circular permutations. And so we have to kind of have it in our mind. You can memorize it, sure, right? But it's n minus 1 factorial. Okay? Because you force this first person to sit down, right? And then you have 3 minus 1 left over, and then you decrease from there. Let's see. In how many different ways can 5 people be seated at a circular table? So now my n is 5. And if you want, although I find the slots kind of confusing in a circle because I have a hard time drawing the slots kind of normally, but we can start 1, 2, 3, 4, 5. That looks weird, but remembering that the first one, we just pick someone, we force someone to sit down, right? And they're the placeholder. Because it doesn't matter which way you twist this circle, it'll stay the same. And then I have 4, 3, 2, 1. To choose from. Which would be 1 times 4 times 3 times 2 times 1. Because we've already used, so here, this 5, right? 1 goes here. And then start with 4. Or if you prefer, or if you remember it, n minus 1 factorial. Right? So you can use the slots just like we've been doing, or it might just be easier to memorize the n minus 1 factorial. Right? In this case. 5 minus 1 factorial is 4 factorial, which is 4 times 3 times 2 times 1, which is the same, which is 24. Oh. Nice. Good. Any questions about that one? I should point out, you don't have to draw your slots in a circle like this. If you want to, because the key here is that you just place a person, right? And so if you remember to do that in your slots and you just make your first one a 1, and then 4, 3, 2, 1, right? You're just back to the regular slots. I just wanted to show you the visual of the circle. In how many ways can 4 couples be seated at a round table if the men and women want to sit alternately? This means that I have 8 people, which means I have 8 positions on my circle. Now, can I pull that off? Start with the top. 1, 2, 3, 4, 5, 6, 7, 8. Sort of. I should have done it down here. Got a little crowded. That's okay. It's hard. We're going to use the same trick. Force a person to sit down and start there. Right? And so now, depending on if this was a man or a woman, that'll determine who has to go here, how many I have to choose from here. Now, for simplicity, although kind of boring, let's say there are 4 men and 4 women. So if this is a man, then I have 4 women that I could put here. Right? And so I could go for 4 women. Same scenario. If this was a woman, I have 4 men that I could put there. Right? Now, we don't consider them being separate because we're just putting a person down, same as we have been before. Then, if I'm alternating, then I have 3, then 3. That's the tricky part. Then 2, and 2, and 1, and 1. And if I go around, circle this way. So, or we could write, force the first person to sit down. 1, 2, 3, 4, 5, 6, 7, 8. Then I have 4 people, and then I have 3, and then I have 3, and then I have 2, and then I have 2, and then I have 1.
It has been long, saw the 8 people, and then we didn't think to split up the men and women and do like 4 and 4. Even though technically, yes, it's just couples, but if my brain hypothetically wasn't working. If I did like one at the top, and then I did 7, 6, 5, 4, 3, 1.
I can see that, but because it says if the men and women want to sit alternately, then we have to take that into account. I'd give you part marks though.
Okay.
If it was on the test, I'd give you part marks. What I'm really looking for here is that you, in a circle, you know that you just put one down first and kind of clear that out of the way. Nice. Good.
Would it tell us on the test if it was like a circle?
Yeah. Yeah. Yeah, so it'll say like at a round table or something like that. Yeah. Or I tend to use the word circle just to emphasize that, hey, this is a circular problem. Right? Because at a round table, you might just be reading fast and read table. Right, and then, but so I tried to make it. Just like with the explanation of the circular table, permutations with similar elements has a lengthy discussion in the textbook as well. Okay, so here, see the textbook for a longer explanation. Yeah. But for us, because for me, I don't find that the longer explanation helped that much. And so for me, I just remember to do what this formula says. Okay. So let's just talk about it. But if this formula, if you want to know why is that, then you can look in the textbook, read the textbook. So the number of permutations of n elements taken n at a time with R1 elements of one kind, R2 elements of another kind, and so on, is going to be n factorial divided by R factorial times R1 factorial times R2 factorial, blah, 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 blah. So all the duplicates. What this means, so if there are similar elements, we divide by that number of elements factorial. And we divide n factorial by the number of similar elements factorial. I think if I show you an example, it'll be more clear than the words that I just. So when we talked about the permutations of the word article, right, we had some restrictions on that, but there was only one of each letter, right? Now, the problem with a word like Mississippi, find the number of different permutations of the letters of the word Mississippi, is that this I is going to read the same as this I, right? And this I, and this I. And so even though technically you could assign them and let them be different I's, I1, I2, I3, I4, for example, right? They still make the same word. So what we're going to do is first I'll move these down. First, count how many letters total. So here, step one, n factorial, or n, is the total number of letters. So in this case, we have, let's see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. Now, you want to count how many of each letter there are. So step 2, count how many of each letter there are. I like to list all of them. There's one M. In fact, what I'll do for this one is kind of blow it up and cross them out as I go. Because I want to make sure that I catch them all. We said that there are 4 I's. 1, 2, 3, 4. 1, 2, 3, 4. S. 1, 2, 3, 4. 1, 2, 3, 4. And finally, P's. There's 2 P's. You'll want to make sure that these all add to 11. They do. 8, 10, 11. So here. Make sure total is 11. Think. Now, take the total factorial and divide by each of these as a factorial, multiplying together. And so now, step 3 is take the total as a factorial in the numerator, so that's the top, and divide by each letter count factorial. I'll say in brackets in the denominator. There. So what that's going to look like is 11 factorial divided by 1 factorial times 4 factorial times 4 factorial times 2 factorial. So 1 factorial, 4 factorial, 4 factorial, 2 factorial. Usually we don't bother writing the 1 factorial because it's just 1, right? And so usually we kind of skip that part, but technically it's there and it's okay to put it there, right? So since 1 factorial is 1, we don't need to write it. But it's technically not wrong to write it. $11 factorial, if you have a factorial button on your calculator, now might be the time to find it. I get 399,16800 divided by 1 times, let's see, 4 factorial is 24 times 24 times 2. Which puts me at 399,16800 divided by 1152. which gives me 34650. 34,650 different ways or different permutations of the letters in Mississippi. I think once you kind of see, okay, so I take my total number factorial and then I divide by however many repeats I have, factorial. I kind of divide them out. Wait, grab another. Using what we just learned, how can we reframe this question to be the same as the question we just had? Right? And so if a coin is tossed 6 times, how many different outcomes consisting of 4 heads and 2 tails are there? So what you can do is you can say, okay, well, what if I rewrite this for heads, 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 tails, tails, right? And that can be our new letter or word, I guess. So that's going to be the trick, is if you have similar elements, then you can just write them out as if it's a word. And so, or pretend heads, 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 tails, tails is a word. And repeat what we did earlier. Which means that we have 6 total. And I want to splice out 4 duplicates and 2 duplicates. I guess they're quadruplicates. So duplicates. If you don't have a factorial button on your calculator, here's a trick. Remember how we wrote out 6 factorial until you hit the factorial in the denominator? What you want to do is you want to write it out until you hit the bigger factorial. So in this case, 6 times 5 times 4 factorial divided by 4 factorial 2 factorial. Since I'm just multiplying and dividing, this 4 factorial and 4 factorial cancel. So now 6 times 5 divided by 2, I'm going to go with 15. But I'm going to confirm because it's late. Yeah, I didn't bother because I would have to write out till 4 factorial, but you could, yeah. Nice. In how many different ways can 4 nickels, 3 dimes, and 2 quarters be arranged in a row? We can just pretend it's a word. N. Can't remember how many I said. D. Q. Make that a word and just do the same thing. You don't have to pretend it's a word. I find that it's easier to look at, right? And so if we have nickel, 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 dime, 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 Q, Q, quarter, quarter. I have 4 plus 3 plus 2 total, which puts me at 9, right? So I have 9 factorial divided by 4 factorial, 3 factorial, 2 factorial. Let's do the same trick where I write out 9 factorial till I reach 4 factorial. 9 times 8 times 7 times 6 times 5 times 4 factorial. Didn't save me a ton, but it'll save me a little bit. Right, divided by 4 factorial, 3 factorial, 2 factorial. These will go away, the 4 factorials. Now, oh, I did something weird with my calculator. 9 times 8 times 7 times 6 times 5. $150. And 3 times 2 times 1 times 2 is divided by 12. Because 3 factorial is 6 and 2 factorial is 2. Good. I get 1,260.
Then because when you cross the 4 factorial out.
Yeah.
Could you then do 98765 factorial and then cross the 3 factorials up and then do it for 2 and cross the 2 factorials up and then you just have 9 times 8 times 7 times 6 times 5. It kind of sounds like a lot of work, but it sounds like less work than writing it for these 7.
Before I commit to an answer, do you mean saying that, hey, I know that 3 factorial is 6 and cancel those?
No, I mean like, because you went 9, 10, 7, 10, oh my gosh, 9, 10, 8, 10, 7, 10, 6, all the way down to 4.
Yeah.
Factorial. And then you crossed out the 4 factorial.
Yeah.
If I did 9, 10, then since those 4 factorials are crossed out, could I do 9 times 8 times 7 times 6 times 5 times 3 factorial and then cross out the 3 factorial from the top and the bottom? Does that make sense?
You cannot, because this is just a 5.
But if I went down from 5 to 3 and jumped over 4 because we crossed out the 4.
Oh, but here, so this 4 factorial is taking the place of 4 times 3 times 2 times 1. So they're all gone. They're all. But this is why I wanted to make sure. If you recognize that 3 factorial is 6 and you want to cancel these 6s, that would be allowed. But it's not something that I would expect you to do. So I'm going to erase that, but you would be allowed to do that. Right? Let's see here. Just because that might be confusing. Yeah. We already, whoa. We already, why doesn't my Apple Pencil work? Well, because I throw it around, I guess. We already kind of introduced this sneaky trick, and I think that's fine. But yeah, you could cancel those 6s if you wanted to. How am I doing? We only have 2 more examples, and they're all the same. We can do it. Let's just do it. And then you'll have the shortest video ever on, well, whenever I make it. A stockbroker wants to assign 20 new clients equally to 4 of its salespeople. In how many different ways can this be done? Now, what that means is, let's call these 4 salespeople A, B, C, and D. That looks like a P, D. I guess it could be a P, but it's weird. What that means is each of these people gets 5 clients, right? And so 5 go to A, 1, 2, 3, 4, 5. B, 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 and so on. Why am I not writing them all out? Because they'll all be the same, right? And so you can write them all out, but I'm trying to end on time here. 20 factorial, 20 clients split between 4 salespeople, which means I have 5 factorial, 5 factorial, 5 factorial, and 5 factorial. There's no. Does everyone have a, yeah, exactly. Yeah, it doesn't really, so it's going to be huge. And I'm just gonna go ahead and use my calculator with my factorial button and just jump to the answer. Syntax error. Well, that's no fun. It's still huge. 1.173274502 times 10 to the power of 10. Huge. Because there's a flagpole one on your assignment, let's do this one. A shopping mall has a straight row of 5 flagpoles at its main entrance plaza. It has 3 identical green flags and 2 identical yellow flags. Now we're back in kind of easy territory here. So we've got green, 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 yellow, yellow. How many distinct arrangements of flags on the flagpoles are possible? 5 factorial divided by 3 factorial, 2 factorial. Now we're talking. 5 times 4 times 3 factorial divided by 3 factorial, 2 factorial. 20 divided by 2, 10. Good job, guys. All right. We only have one more section, which I'll have in the video, combinations, where order doesn't matter, and that's the only change. And then I'll see you the following week, not next week. If you have any, that's crazy. For test review, where we'll go through the practice test that you'll have soon.